I will describe Chua circuit for nonlinear dynamics. The Chua circuit is another important circuit in the study of nonlinear dynamics. The circuit is the following. L is a coil and inductance of about 20 millihenries. C2 is a capacitor of 0.1 microfarad. C1 is a capacitor of 0.01 microfarad. R is a 10-turn 2K pot. The important point is that the resistance of the inductance must be less than about 25 ohms, and NLR is a nonlinear negative resistance. This is the heart of the Chua circuit. This nonlinear resistance has the IV characteristic shown here. I is plotted along Y and V along X. You see that I decreases as V increases. So it is a negative resistance, and the slope of IV curve changes at the point minus VB and plus VB. This is nonlinear character. How do we build a nonlinear negative resistance? First, take an op-amp circuit shown here. You have the op-amp with the non-inverting terminal connected through a resistance R1 to the output terminal, an inverting terminal connected through the same resistance R1 to the output terminal, and the inverting terminal is connected to ground through a resistance R3. If we now apply a voltage V between the two terminals, plus and minus, a current flows. The variation of I with V for this circuit is shown here. IV characteristic has a positive slope when the applied voltage is below minus VB or above plus VB. But between minus VB and plus VB, current decreases with resistance. It has a negative resistance. The slope of the positive part of the curve has the value 1 by R1. It is determined by the resistance R1. Between minus VB and plus VB, slope is negative with a value minus 1 by R3. When you increase R1, the positive slope decreases. So the curve becomes more and more closer to the horizontal line, and the break voltage VB moves closer to 0. So the effect of increasing R1 is to make the positive slope small and the break voltage come close to 0. What we want is a negative characteristic with two different slopes. What we have here is a negative characteristic with a single slope. To make a negative characteristic with two slopes, we make two circuits. The first circuit with R1 dash is 22K and R3 is 2.2K. And the second circuit with R1 is 220 ohms and R3 is 2.2 K. The first circuit will have a break voltage VB dash of 1 volt. That is between -1 and +1 volt, the slope will be negative. Beyond -1 and +1, slope will be positive. For the second circuit, the break voltage VB is 5 volts because R1 is smaller than R1 dash. The positive slope of the first circuit is 1 by 22 K, while the positive slope of the second circuit is 1 by 220. So second circuit has a positive slope 100 times larger than the first circuit. The negative slopes of both circuits will be -1 by 2200 because R3 is the same. If we now put the two circuits in parallel and connect them to a voltage source, the current drawn against the voltage will show this characteristic. If one is below -VB or above +VB, you have a positive slope which is almost equal to this value. Between -5 and -1 volt, the second circuit has a negative slope, first circuit has a positive slope. Sum is negative, and so you get a characteristic with a negative slope, close to -1 by 2200. Between -1 and +1 volt, both circuits have negative slopes -1 by 2200. So you get a negative slope for the combination which will be -1 by 1100, twice as large as this. Again, between +1 and +5, you have a negative slope -1000 to 1 by 2200 plus 1 by 22,000, and beyond VB you have a positive slope. So between -5 and +5 volts you have a non-linear negative characteristic. To measure the IV characteristic of the nonlinear circuit is the first part of the experiment. For this, we put this switch on the Chua circuit. We put this switch up. When we put this switch up, you see that this nonlinear resistance is disconnected from the rest of the circuit. So to measure the IV characteristic of NLR, you must disconnect it from the rest of the circuit, and you do it by putting this switch up. The two ends of the nonlinear negative resistance come to the 2 points A and B, the yellow and the blue banana terminals. We connect a DC power supply which can go at least up to 10 volts. We connect the positive of the DC power supply of the DC power supply to a DMM which will measure the current in milliampere range, DC current in milliampere range. The negative of the DMM is connected to A. B is connected to the negative of the power supply. So the current will go through the ammeter, through the nonlinear resistance and come back. To measure the voltage across AB, I connect a second DMM which is put to measure the voltage to 2 decimal places. So I switch on my power supply, set a voltage of about 6 volts. There is a switch behind the Chua circuit, you must switch it on. The voltage across AB is 6.06 volts and the current through the circuit is minus 1.01 milliampere. We have to start the measurements from minus 6 volts and go to plus 6 volts. To get negative voltages, I interchange the connections to the power supply. Now, the voltage across AB is minus 6.04 volts and the DC current is minus 0.05 milliamperes. I will now change the voltage from minus 6 to minus 5 gradually. And you can see what happens when I change the voltage. The current which was negative at minus 6 volts becomes positive and increases to a value plus 2.25 milliampere at a voltage minus 4.8. So up to minus 4.8, minus 6 to minus 4.8, the voltage is increasing, current is also increasing, so the slope is positive. Now I change the voltage further from minus 4.8 to minus 2. You see current has come down from 2.28 to 1.16. The voltage is increasing, current is decreasing, this is a negative slope. So what one does is you start with minus 6 volts, note the voltage and the current, note the voltage and the current, then change the voltage from minus 6 to minus 5.8, minus 5.6, steps of 0.2, note the current, till you come to 0 volts, close to 0 volts. Then you interchange these two terminals. Now the voltage will be positive. Now you increase the voltage, this positive voltage, and note the current, and you do this up to 6 volts. So from minus 6 to plus 6 volts, you measure the current in steps of 0.2 volts. You change the voltage and you measure the current. You plot the current versus voltage, then you get this characteristic. You see that when the voltage is less than minus 5 volts, you have a positive slope. When the voltage is more than plus 5 volts, you have a positive slope. Between minus 5 to minus 1 volt, you have a negative slope, and between plus 1 and plus 5 volts, you have the same negative slope. Between minus 1 and plus 1, you have a much larger negative slope. The slope is the negative slope between minus 5 and minus 1 and plus 5 and plus 1 is minus 4.18 10 power minus 4 Siemens, and between minus 1 and plus 1 slope is minus 7.71 10 power minus 4 Siemens. This is the heart of the Chua circuit, and it is very easy to make with an op-amp, very cheap to make. Now I will disconnect the power supply. I will put this switch down to connect the nonlinear resistance to the rest of the circuit. And I will show you what happens as I change the resistance of the pot. This is the 2K pot. There are two banana plugs, O2 and O1, O2 and O1. O2 is connected here. So between this point and the ground is this, so between O2 and the ground, I will get the voltage across C2. O1 is this terminal that is connected here. Between O1 and the ground, I will get the voltage across C1. I will measure the AC voltage across C2, AC voltage across C1 by connecting C2 to channel 1 of the oscilloscope, C1 to channel 2 of the oscilloscope. I put the oscilloscope in the XY mode, that is, voltage across C2 moves the electron beam along X, voltage across C1 moves it along Y. I have to put C1 in AC coupling. I have to put C2 in AC coupling. And then I put this pot at the extreme left. When I put this pot at the extreme left, you see that I get a dot at the origin. That means no AC voltage comes across C2, no AC voltage comes across C1, there are no oscillations. Now I will turn the pot and you will see what happens. At one point of the pot, you will see a loop appearing on the oscilloscope screen, and this loop I am changing the scale of X and Y. I have put X at 200 millivolts per division and Y at 500 millivolts per division. Now what does the loop mean? It means you are getting an AC voltage across C2, AC voltage across C1. The loop is single. It means the frequencies of the two AC voltages are the same, and this you can see if I put it in the YT mode and I reduce the time scale. You see the AC voltage across C2 is the yellow line, AC voltage across C1 is the blue line. They have different amplitudes, they have different phases, but they have the same frequency. If you measure the time between the two peaks on the yellow, it will be the same as the time between two peaks on the blue. The frequency of oscillation is around 2.75 kilohertz. Now I will turn the pot a little bit more. Now you see that you get an image with two loops. Each loop represents one cycle. The two loops are different. That means the voltages across the capacitances in the first loop is different from the voltages in the second loop. Also, the period of oscillation is different. So the first cycle, the period is T1. Second cycle, the period is slightly different, T2. So the circuit goes through the first cycle, goes through the second cycle. The third cycle again has period T1, fourth cycle has period T2. So the cycles are performed with period T1, T2, T1, T2, T1, T2. This is bifurcation which you saw on the Feigenbaum circuit. What are these curves? These curves are called attractors. If you perturb the voltage on C2 or C1 by a little bit, then over a period of time you find the voltage will come back and you will get this curve. So this is called an attractor, and the attractor is a double loop showing bifurcation. I will now turn further. I will stop. You now see four loops. You now see four loops. Okay. You now see four loops. That means you now have four cycles performed with the period T1, T2, T3, T4, and this is repeated again and again. You have a second bifurcation here. Two loops have become four, same as you saw in the Feigenbaum circuit. What is happening when I am changing the pot? When I am changing the pot, the voltage across C1 increases. You will see that the voltage across C1 is the same as the voltage across AB because the switch connects this nonlinear resistance to C1. So as I turn the pot, the voltage across the nonlinear resistance increases. So initially, when you get the single loop, the voltage across the nonlinear resistance is between -1 and +1 volt, so the characteristic has a single slope, only a single slope. It is linear, you get one loop, one frequency of oscillation. As I turn the pot, the voltage across the resistance increases and goes beyond the point -1 volt and +1 volt. Now the voltage oscillates from something like -1.5 volt to +1.5 volt. Then part of the characteristic has a different slope from this. Non-linearity starts making its appearance, and that is the reason why you get bifurcations, which are signs of non-linearity. Then bifurcations will start very fast. I won't be able to see the bifurcations. But you now see a loop which looks like this. This loop, each loop corresponds to one period of oscillation, but you see that this loop goes more, the voltage across C2 goes more to the right than to the left. So the voltage across C2 has a DC value about which you get AC oscillations. If I put it in the main mode, you will be able to see this. You will see that the blue is voltage on C1. So the blue here goes more to the negative at the two ends. I can increase this, show it more clearly. You can see the blue goes more to the negative and less to the positive. So the voltage on C1 develops a DC voltage about which you have oscillations. This attractor is called the Rossler attractor, after the name of a person who found this attractor. I will turn this pot some more. And now you will see the figure here is turned 90 degrees to this figure because I have connected the channels in a different way. But however, what you see here is that oscillations are taking place about the negative voltage of C1, and then the DC voltage changes to a positive voltage. Oscillations will take place about this voltage, and then they go back and forth from left to right. You can see that on this, if the oscillations, look at the blue lines, these oscillations at the left and at the left are above zero. They are taking place about a positive DC value. These oscillations are below zero. They are taking place about a negative DC value. So the positive DC value shifts here, and you can see the shift taking place like this. So this is called a double scroll attractor. It is scrolling about this point, then again scrolling about this point. So it is called a double scroll attractor. The voltage on the nonlinear resistor is increasing. It is single loop, it is between -1 and +1 volts. Then as I reduce the resistance, it goes beyond -1 and +1 towards -5 and +5. Ultimately, when I turn this pot more and more, it will reach a value which is equal to -5 to +5. Channel along the y-axis is 2 volts per division. This is 0, and you see this is 1, 2, 2.5 and 2.5. So it goes between -5 to +5. It exhausts the negative resistance region. At that point, you get this loop, which is called the limiting loop. So, the Chua circuit shows not only bifurcations, the period becomes doubled, then becomes 4 periods, 8 periods. Not only shows the bifurcations which we saw in FEIGENBAUM circuit, but here our attractor is a curve in 2 dimensions, and the shape of the attractor keeps changing as you increase the nonlinearity. You first get a bifurcation, 2 loops, then you get another bifurcation, 4 loops, then many loops, but some of the loops are not symmetric. Then you get scrolling about a positive DC value and scrolling about a negative DC value, and finally you get the limiting loop. So not only does bifurcation take place, but the attractor in 2 and higher dimensions, the attractor will keep changing its shape as the nonlinearity increases. The Chua circuit is a very basic circuit. Along with FEIGENBAUM circuit, you will find the Chua circuit described in the very first chapter of any book on nonlinear dynamics.